Tired of waiting in long Starbucks lines, always ending up coming late to class? Well, don't let this be you anymore. With our new product, the Coffee Connection, you can get the most out of your coffee machine at home or at work. Our custom coffee machine is fully integrated online, so you can use our custom app to check the level in your coffee machine anywhere, anytime. At home or at work, you'll always know how much is available. It even updates automatically, so you know how much coffee you have at the push of a button. Not only can you check the levels, but you can control your coffee machine from our app. With our convenient on and off buttons, you can turn off a coffee pot that's been left on over the weekend, or get it started in the morning so there's a fresh cup of joe waiting for you right when you get to work. See how it turns off from anywhere at just the click of a button? It's just that convenient. But we need your help to make the Coffee Connection a reality and reach our $50,000 goal. There is still a lot of work to be done, and we want to internalize all of the hardware and have the machine Wi-Fi enabled so that the only cord is the power cord. We also still need to develop our free app to be available in the Android and Apple marketplace. We have a number of different exclusive offers that can be yours with just a small investment. For $20, you can support us and get a bag of our premium signature roast coffee. For $50, we'll give you all of our code, diagrams, and parts lists so you can turn the Coffee Connection into your own do-it-yourself project. For $100, you can get your very own Coffee Connection as soon as production begins. And finally, for $300, you can have all of the prizes, and you can choose your very own color of Coffee Connection as well as personalized engraving. We hope you'll decide to support our project, and soon, this could be you every day. To start this project, our first goal was to hack into this power strip and replace the on-off switch with something we could control with the Arduino to control the coffee pot from the internet. We hollowed out two of the outlets and added in a toggle switch as well as a solid-state relay, which connect into what was the original switch by the two black and the two red wires. The toggle switch on the left has on and off modes that serve as the same purpose as the original switch on the power strip, but now there's also an Arduino mode which engages the solid-state relay. The solid-state relay is controlled by the two yellow wires and only allows current to pass through the power strip when it's given a 5-volt signal across its leads. Here is where the system is soldered into the original switch leads, and here is the toggle switch from the outside of the power strip. It turns out that the Arduino did not have enough power to trigger the solid-state relay, so we improvised with this gray box which has some components to boost the signal from the Arduino. Inside, a 9-volt battery powers a 386 op-amp which gives a times 20 gain to our Arduino signal. We then even out the signal with a read relay that gives us a nice 0 or 9-volt signal for our solid-state relay. On top of that sits the Arduino and the Ethernet shield, which allows us to input an internet signal into our Arduino. Here's the completed power strip setup, which turns on and off in response to a signal from our server. And this is a circuit board block diagram that clearly lays out all of the components of the system. The Arduino uses a secured data string to connect to the PhysGL server. There it accesses our cloud storage and checks whether or not there is an on or off signal sitting on that location. Once it has the data, it interprets it and sends a corresponding on or off digital signal to the power strip. The Arduino checks the server about once a minute to see if any change has been requested. In order to measure how much coffee is in the pot at any given time, we hacked into the machine and added an array of photoresistors in order to measure the coffee level. These 4 photoresistors respond to changes in light, so when black coffee reaches and covers them, we know the coffee has reached that level of height. The wires feed through the interior of the coffee machine and come out of the back where it meets with our Arduino pack. In here is another Arduino Ethernet shield setup, which takes the light data and sends it to our server online. This block diagram shows a layout of all of the components of this part of the setup. The Arduino code initializes all of our input pins and connects to a different part of the PhysGL server in order to upload the data. The code uses if-else statements to interpret the light readings from the photoresistors and export them as an integer that corresponds to the amount of coffee in the pot. The code uploads this integer to the server about once every 8 minutes. Here is some video of the visual interface responding as the coffee pot fills. We can see as that various photoresistors are covered, it's expressed on the visual interface as the levels also increase. When the pot is full, you can see that the same thing is shown online, and you know a cup of coffee is waiting for you right when you get to work. We are currently using the PhysGL server to host the visual interface component of this project. The code first looks at the data uploaded by our Arduino sensor array and produces a graphic that corresponds to the amount of coffee in the machine. When one of the on or off buttons is pressed, this code saves that data to a cloud storage site, where our Arduino looks to see if it should turn the power strip on or off. The black level shows the amount of coffee, and the sphere is green or red depending on what state has been asked of the machine. Here is a picture of the project fully deployed in the physics lounge, where it is helping students get their caffeine even more efficiently. The vast majority of this project was spent working with the Arduino code and attempting to get it online and connect to the server. We spent dozens of hours getting this code running, as we learned the intricacies of using data strings, MAC addresses, and server timeouts, all of which are essential qualities in almost every aspect of this process. We now know a lot about how devices communicate with the internet and the various security techniques they use to prevent hacking. During the process, we even stumbled upon some of our own hacking techniques that allowed us to update to the server even more often than the security protocols dictated. Once we became more familiar with the process, we also decided that this project would require 2 Arduinos to both upload and download data as we required. We were able to get it all running eventually, and it was quite satisfying to see the entire project deployed. The other major obstacle we found in this project was supplying enough current in order to control the solid-state relay. All of this circuitry amounts to a fairly elaborate workaround that was not included in the original plans for the project. Though it did end up being fortuitous to set up this second box, as it eventually housed our second Arduino Ethernet Shield setup. All things considered, this was a satisfying and empowering project that really displays some of the functionality that can be used with an Arduino setup.